Polymers are described as one of the greatest inventions of modern times, but also the worst. Because they are the things that are designed to be hardy and cheap. And they don't tend to break down easily. Most things, if you leave them in sunlight or you expose them to heat, they will break down rapidly. Some types of plastics will outlive civilization. And we use them because they are cheap. Above all else, we use them because they are cheap to manufacture. So I don't know if anyone knows the process of getting plastics from fossil fuels, but that's how we get them. So we take fossil fuels, we use more fossil fuels to extract the plastic and not the plastic, it's not plastic in there, but it's a form of hydrocarbon in the oil. We then use plastic, we then use fossil fuels to treat the plastic, to turn it into plastic pellets, to make it into polymers, to make it into what we see in your kitchen, in your lunchbox. And it's because of this versatility, the ease of cost, and how easy they are to manufacture. If we didn't take them out of the oil, the crude oil that we extract, then it would just go in the bin. So the companies are going to want to extract as much as they can, and they're not going to waste it. Without plastics and this cheap ability to produce them cheaply, we would not have, the cost of things would be astronomical compared to what they are now. So polymers, cling wrap, detergent bottles, a bottle of barbecue sauce from Aldi because it's cheap. All made from polymers. Polymers are long chains of monomers. Mono being one, poly being many. And there's different kinds and we use them for different things. But we generally refer to them as plastics. If we did the organic chemistry seminar with me, we would have gone through biopolymers, which are proteins. But here we're talking purely about hydrocarbons and these long chains that we can manipulate to make into plastic. So, as I said before, poly was one. I mean, poly equals many. Mer equals parts. Monomer is one. Poly is many or more than two monomers joined together. We call that this polymerization. So polymerization is the creation of polymers through the addition of one monomer onto another. So many monomers make a polymer. What I want you to do is go into your kitchen and find 3 or 4 things that are plastic. Whether they be Tupperware containers, whether they be plastic bottles, whatever. I'll give you like 2 minutes to find them. Here's the method to my madness. Maybe I just want you to run to your kitchen. Who knows? So I've got a bottle here. See if I have got it. I bet it won't. It looks silly. Try and find Tupperware container. Yeah, but that's not going to say what. Tupperware containers are good. That's long enough. Everybody back? Give me a thumbs up. Anybody actually leave? Everybody still go. Is everybody back? Sorry, apparently Izzy just put toothpaste all over the keyboard. I did say just get the plastic things, didn't say squirt toothpaste everywhere. Madison? Wow. You're gonna kill me. Madison. Madison's going to make her own plastic, apparently. Okay. So, we're not going to use them yet, but I thought I'd take a look. So we add monomers together to create polymers. So we take ethene, which is this. And those who've done organic chemistry will know what ethene is. Has the double bond between the two carbons. We add them together, usually under intense heat, and usually with a catalyst to break the double bond. And then you join them together. You can make them up to 20,000 carbons long. And we can manipulate this to produce things, plastics of differing properties. So usually this tells you, there's a number here, of how many of these monomers are joined together. It's represented like that. So we've all seen polystyrene. So that horrible stuff that comes in anything you buy, anything electronic, it's in there to protect it. Another one of those bane of the existence of Earth. It will outlive all of us. Polystyrene in the atmosphere, in the environment will outlive all of us. If not for the next few thousand years. You can't burn it because it produces toxic gas. And it's through this breaking of the double bond and reforming the single bond that makes them strong. So, styrene and polystyrene. So styrene monomers make up polystyrene polymers. So ethene, polyethene. Propene, I think it's called polypropylene. And tetrafluoroethane is polytetrafluoroethene. Don't worry too much about it, but we just add poly. Okay, on your plastic things you've picked up, and I bet none of them actually say it now. You'll either see LDPE or HDPE. They used to have to put it on by law. Can you see any of that on your plastic? LDPE or HDPE? I bet now they don't do it. Now I look at. No. Anyone else see it? On your toothpaste, is it? Sorry, I shouldn't laugh. Okay. Well, that shows how old I am. You used to have to put, whether it was a low density plastic or a high density plastic on it. If you get a Tupperware container, it should still say this. So we make LDPE or low density polyethylene plastics under high pressure and temperature. And it creates these polymer molecules that they're not in a straight line. They go with these side chains. So you have the backbone, and then you have these side chains. Now I'm going to explain what this means, but I want you to have a think. What effect could these chains have on the properties of a polymer? We also have, oh no, jump ahead. So just the closer the ethene molecules are together, the more tightly packed they are. But if they have these long chains on the sides, they can't pack together really closely. Which unfortunately, well, not unfortunately, this is the way they're designed. So, I was just drinking water out of this. I definitely wasn't drinking out of water. It's just a plastic glass. This plastic cup. We couldn't make this plastic cup without using this method. So the reason that it's squishy and it bounces back into place is because the molecules, just put water on my keyboard, are not packed tightly together. They're packed like this. So this is squishy. If I put a lighter on it, it would melt relatively quickly. It would smell absolutely terrible. It's opaque and it will not conduct electricity. So when we make these polymers, when we take the plastic and we hit it with high temperature and pressure, it creates this. That is low density polyethylene. So we take the ethene monomers, subject them to high temperature and pressure, and they make this. So the forces between the molecules, because they're not packed closely together, is lower. So the melting point is low, they're soft, compared to high density polyethylene. And we create this using a catalyst. So something to speed up and make the reaction happen without ramping up the temperature and the pressure. By ramping up the temperature and the pressure, we make these chains. So we turn up the temperature and the pressure. And the way the molecule is built is this. We do it without the pressure by using catalyst or something to help the reaction happen. we get fewer branches and smaller branches. So the molecules pack tighter together. And there's this concept of crystalline structure. So everyone knows what salt looks like. So things that are packed in an ordered structure, and I think I'll bust out the whiteboard for the first time tonight. Normally longer than this before I get the whiteboard. No, shorter than this before I get the whiteboard out. Got these two molecules are closer together. So the forces between them are higher. So when we do this, we make hard plastic. If we look at, it makes, because it's so ordered, it makes a crystalline structure. So this crystalline structure means the melting point is higher than say there. So there's only 2 points of contact here because the rest is too far away. Here, there's lots of points of contact because it's closer. So the forces holding the low density are stronger than the forces holding the high density together. Because the arrangement is more ordered. So, let's find an example. The plastic on the outside of this cup would be high density. It's hard, has a high melting point, it doesn't bend. Generally more rigid because it has more structure. So if we remember back to our organic chemistry, when we add more monomers together, so more monomers, or in this case, more carbon atoms in the backbone, the melting point and the strength of this plastic will go up. And we then get to a point where we can make plastic that is so strong that it can be used in bulletproof vests. So a couple of centimeters thick of what we call molecular weight. Ultra high molecular weight polyethylene. Actually, what's in your helmet, on your bike, on your motorbike helmets as well, it's actually stronger than a lot of metal. So they make artificial hip joints out of this stuff as well. You can make boat hulls that can crash into things and they won't bend and break in the same way. So ultra high molecular weight polyethylene or polyethylene. biggest problem with the LDPE when they make things like water bottles is the structure is not very strong. It's not held together very well. So you leave a water bottle in direct sunlight, in heat, the water heats up and begins to break down the plastic. And the plastic is not, I mean, it's not great for you. But it's all the additives to make the plastic have its properties. So I don't know if you've heard of things like BPA, bisulfonyl A, which is a endocrine disruptor. But when we take HDPE, we can make, so PVC pipe is used for plumbing because it is a HDPE because it's highly crystalline, or there's a very uniform way that all of these molecules line up. They line up all the same. And they create this ordered crystal lattice structure that makes it very strong. So pipes, buckets, food containers, and most fuel tanks, I mean, fairly logically, are not made of metal. They're made of this HDPE plastic. And it's because of this highly ordered crystalline structure that you can get that strength and it won't break down. So I will just use the whiteboard. I'll use the slides to discuss this one. So polypropylene, we make it from a propene. Well enough. I remember how I said that how the molecules are ordered together, or how they're stacked together in this crystal structure determines their properties. So over here we have what we call isoactic. We have actactic and then syndiotactic polypropylene. And you can see that is to do with the distribution of these side chains. So there needs to be a to make it crystalline and strong, there has to be a highly ordered structure. So it has to be the same. And if we look at isotactic, all the groups are on one side of the polymer chain. So that you get this regions of crystallization. It's not particularly strong. We use it to make baby bottles, Australian banknotes, thermal underwear, and polar fleece jackets. When there's atactic, that's when the side groups are completely random in their distribution. And we know that in order to be crystalline, they have to be the same. Each molecule has to be exactly the same. So this syndiotactic is where we put the side groups on regularly alternating sides. So they're changing on their sides, but you can see it's like a never-ending double. It's consistent. And this is where we get polymers where we can make bulletproof vests out of plastic. Because they're so tightly packed together and consistently packed together that they oh, my brain. So it's so tightly and consistently packed together that they almost have a perfect crystalline structure. So we can manipulate the properties of the polymer. So we can take propene, polymer, it's polypropene. So dishwasher safe plastic, ice cream containers, we can make ropes out of it. One you might know is Teflon. So we've taken the hydrogen off here, replaced it with fluorine, meaning that the Teflon doesn't react with anything. So nothing sticks to the food. I mean, the food, nothing sticks to the pan. The food you're cooking doesn't stick. So you could leave something on there and nothing would happen. It would burn, but it wouldn't stick to the pan. We've done the same thing here, but we've added chlorine instead of 2 hydrogen, and it sticks to itself. So cling film. PVC, we've added hydrogen, we've added a chlorine molecule here instead of a hydrogen. The one you parents might know might be vinyl. The vinyl floor, the old houses they used to put in the old houses. Old, they used to use it for kitchens because it was waterproof and you could drop things on it, it wouldn't break, or you couldn't cut it. What? So if I change one of these side groups, the thing that's going to happen is it's going to change the size of the molecule. And it's going to change the forces between them. So propene nitrile is used in a lot of synthetic fiber. So this is the bad one. Phenylether. So we've replaced the hydrogen with phenol. It is hard and brittle, and it will just about never break down. Superglue. So when superglue comes into contact with the air, so if we look at, we have methyl cyanoacrylate. So that is present in the superglue as a monomer, as a liquid. When you put it on something and it contacts with the air, it polymerizes in contact with the water vapor that's in the air, or on your skin, or whatever you're putting it on, and then it goes hard. So it's a monomer as superglue. As soon as you expose it to water, it polymerizes and becomes hard. So Perspex is the bottom one there. So methyl 2-methylpropanoate. It is transparent and it's strong. So all we've done is change one or more of the side groups of these hydrogens. And we've all of a sudden produced completely different compounds. So I'm going to talk about these on the board because I apparently didn't. I decided that I was going to save my presentation. It would just be a skeleton. So why not? So condensation polymer. So that was an addition polymer. So it's fairly simple. Condensation. So we had a monomer. We get water plus our polymer. So condensation is water. So you have the reactive end group of this. Reactive end group of this one. You end up with water and then the polymer. And water is a byproduct. So that's what condensation, polymerization means. So what do you think? Based on what we've spoken about, what are some applications? Characteristics of polymers. So useful characteristics. So they're generally lightweight. They're hardy, durable. Some HDPE plastics can conduct electricity because they're packed in such a crystalline way that they can conduct electricity. They do not corrode. So eventually over time, car's chassis or body will corrode. They have a low cost. To produce them doesn't cost a lot because we're already pulling the oil out of the ground. We're pulling the oil out of the ground, so we might as well use it, I guess, in some ways. And when we're talking about lightweight, they have a high weight, or they have a high what's called a modulus rating, or high strength to weight ratio. They are lightweight, but they are stiff. Compared to metals with the same strength, they are significantly lighter. So we can take that to make new, we can use in boats and planes and things like that where they may be using metals to make the plane heavier. Whereas if we can replace those with one of these ultra high molecular weight polymers, then maybe we can save weight. So if we look at this, the crystallinity, again, another property. The more closely and consistently packed the molecule, the more crystalline it is. So when we know we subject it to high pressure or a low density, then you get these long side chains and it doesn't pack together. So the tighter and more consistent the molecules, the more likely they are to be stronger. So there's the two properties of polymers, the chain length and the side groups. So the chain length refers to how long the carbon backbone is. And the longer the carbon backbone, generally the stronger the plastic. The longer the backbone, the stronger the forces holding these two carbon molecules together. So the forces holding them together are stronger, the longer the backbone. Except when I have this is our nice crystalline structure, nice long backbone, it's going to be super strong. But if I start sticking chains along here, coming off the backbone, then those molecules are not going to be nicely stacked together. Just not going to happen, and it will not be a crystalline structure. we also have the arrangement of the side groups. So the arrangement of the side groups, if I have my carbon chain here, and all of them have the same, one here, they're going to pack together nice and close. If the next one comes along, it's got a side chain here, a side chain here, and a side chain here, then there's not going to be a crystalline structure. And the longer these side groups are, the further apart the molecules, and the lower the forces between them, so they will not be as strong. So we have these additives. They're called polymer processing additives. And some of them can give sort of BPA, BPE, I think BPO, are all added to plastics. All of them are really toxic. This one is toxic at parts per billion. And it's why that most single plastics, cans, should never ever be reused. You drink out of a plastic water bottle, put that plastic water bottle in. So these are what's called additives, or polymer processing additives. Some of them make the plastic harder. BPA makes plastic more durable. So you can squeeze a water bottle, you can break it. But if you leave it in the sun and it heats up, then the BPA can begin to leak out. They make the plastics tougher, fireproof them so they really can't catch on fire. You might want to make the plastic into a vinyl. And usually they are also designed to reduce cost. So they might reduce the cost and the processing time, but most of them are toxic. And most of them are present in the plastic when it's finished. So when you get it, so that's why, you know, Chinese takeaway containers aren't so bad. But water bottles, no, I can only think of water bottles. Anything that's designed to be single use should be used once. It's not very good for the environment, but I'd rather that than ingesting some of the plastic additives that they add now. So, advantages and disadvantages. So, last advantages, disadvantages. They're cheap to make. Seemingly a never-ending variety. Of new polymers that we can make. Some of them are recyclable. So that some of them can be melted down and remade back into plastic without sacrificing the strength of the plastic. And there's another interesting one. They can replace wood and metal. But we're really just replacing metal, which is mined and not great for the environment, with something else that's not great for the environment. The disadvantages. you do not want to live near a polymer processing plant. Very nasty. Yeah, you don't want to live near one. The byproducts and the products they use are very, very toxic, and it smells terrible. And we make it from oil. I'm not going to write all these down because it's lots of writing. Made from oil, which is a non-renewable resource. And eventually it will run out, and it's getting more and more expensive to extract oil from the ground. And this concept of biodegradable. I had this conversation with somebody who told us yesterday, talking about green chemistry, and how much would people pay to help the environment? And the answer is very little. Most people. There's a certain part of the population that will do everything they can. The vast majority of people, if you said you have to pay 20 cents more for your drink because it's made from biodegradable plastic. A lot of people that would look at the plastic versus paper straw when you go to boosters. How many people go, I don't want the paper straw? Even when it's the same price. So it's this balancing act. And when you burn plastic, I'm sure you stopped burning plastic before. It is really, really, really toxic. And I say that you can recycle things, but as I always say, when you add humans to a really good idea, the idea doesn't work. So people don't recycle properly. Polymers and plastics are still sorted by hand at recycling factories, because some of them, if they were to melt a tiny little bit of a non-recyclable polymer with a recycle, it would destroy all of it. You wouldn't be able to use any of it. So I hope that gave you more, not a hugely sciencey one, but something that is quite relevant nonetheless, and it's one of the big things in the new curriculum. So thank you, everybody. It's been a fun last 10 weeks or so. And I'll see some of you in the exam prep, in the assignment writing seminars. So enjoy the rest of your night.